So let's talk about linear versus Poisson regression. So remember, in GLMs, we don't log the outcome itself, or we don't take a transformation of the outcome itself. We take a transformation of the mean of the outcome. So in linear models, we have our outcome is the linear component plus the error, or we could just write that as the expected value of the outcome is the linear component. In a Poisson log linear model, it's the log of the expected outcome that is the linear part. Log of the expected number of web hits per day is B0 plus B1 times the Julian date. We could reverse that process by exponentiating both sides of that equation and just say the mean web hits per day now depends on E to the linear regression model, okay? So that's the main difference, is that we're going to assume our data is Poisson distributed with a mean, and that mean takes this form, E to the B0 plus B1 times the regressor. Okay, and that's the main difference, though it changes the interpretation a lot. We get a distribution that's much more believable for our observed outcomes, okay? And we get relative interpretations because everything's logged. Our coefficients are going to be interpreted in a relative sense, just like when we log the outcome, though we're going to avoid problems like taking logs of 0 like we had on the previous slide. Okay. Now I want to reiterate, taking logs of your outcomes is actually often a very good thing to do. That's a trick that you should apply not just for count data, but in general in regression. If you have positive data, log is one of the best transformations you can do. It's extremely helpful. The coefficients remain as, if not more, interpretable on the log scale. So that's a great transformation to do. Some of the other transformations, if you square root or cube root data, then it gets hard. Okay, so let's just remind ourselves that the differences that we're looking at are now multiplicative when we transform them back to the natural scale. So if we look at our model, it's the expected value of the outcome is e to the beta naught plus beta 1 times the Julian date. Well, by the properties of expected value, we can factor out beta naught and beta 1 times the Julian date. Now, if we looked at what would be the expected mean for the next day, the Julian date plus 1, right? That would be e to the b0 plus b1 times Julian date plus 1, okay? So divide this by that, and you get e to the beta 1. So our coefficient, e to our slope coefficient, is interpreted as the relative increase or decrease in the mean per 1 unit change in the regressor. Okay? And so if we exponentiate our coefficient, we're going to be looking at whether or not they're close to 1. If we leave them on the log scale, we're going to be looking at whether or not they're close to 0. And again, all these interpretations, when we extend them to the multivariate setting, are just e to the beta 1 is the expected increase or decrease in relative increase or decrease in web traffic, holding the other coefficient, holding the other regressors constant. Okay? So I'm hoping at this point that most of this stuff is kind of old hat for you. Okay, so here's our fitted Poisson regression model overlaid onto our data, and you can see it actually fits pretty closely to the linear model, though it has some nice curvature to it, which is what we wanted. We could have accomplished that in our linear model by adding a squared term, of course, but it's nice to note that a simpler model with fewer coefficients seems to fit the data better. A concern often is that the variance has to equal the mean, so the variance in this case needs to go up as the mean goes up. But here, if we plot the fitted values versus the residuals, it's very clear that the variance is higher for lower mean values. That's a problem. Okay, so we need at least some way to account for the fact that the variance is not necessarily constant. There's a lot of ways to do that, and if you read in the book, one thing that we talk about are the quasi-Poisson models. This model would look at the variance being a constant multiple of the mean rather than being equal to the mean. But in this case, that doesn't appear to be the case in this case, because it looks like we have this issue where there's larger variance for lower fitted values when the Poisson model assumes the opposite. So Jeff actually had this code from this model, the sandwich, which seems like a funny name for a package, but it comes from the sandwich variance estimator, made famous by generalized estimating equations, which, by the way, was a technique that was invented here at Johns Hopkins Biostatistics by two very well-known professors here, Scott Ziegler and Kung-Yi Liang. At any rate, Jeff gives some code here for getting model agnostic standard errors. And if you read in the book, there's a little bit more discussion about this. This is a kind of a more advanced topic than we would like to delve into in this class. However, it's a very important applied topic as well. It's not just a theoretical exercise. So the main point is to do some residual plots to understand whether or not you think your model assumptions hold. Try a quasi-Poisson model, because that's a very easy thing to do in R if you think at least it holds at some level, but maybe not just in the sense of the variance being a constant multiple of the mean. But if it really fails, like in this case, then you have to dig into some other solutions. So in this case, you see here's the confidence interval on the top. If we don't do anything, if we do the model agnostic confidence interval, you get on the bottom. In this case, it actually doesn't make that big of a difference on our. It doesn't make that big of a difference between the two. And again, these are both, of course, non-exponentiated. If you wanted to exponentiate them, which, by the way, I should also mention, exponentiating for a small coefficient like this, it basically just adds 1. So probably if I were to enter this into R, this would be about 1.002, just like before, about a 2% increase on the low end being estimated, 0.21% increase estimated on the low end, maybe at the highest possible, a 0.3% increase per day on the high end. So how do you handle rates? So I should say rates and proportions, because I like to distinguish between rates and proportions. So this is an instance where you have a count, and then you have some offset that should tell you how large or small the count should be. So, for example, if I'm counting failures of my nuclear pumps that I mentioned before, I should have more failures if I monitor them for a longer time. If I'm counting the number of flu cases, I should have more flu cases if I'm looking at a larger population, right? So I should have more flu cases in a bigger city than I would have in a smaller city. So in all these cases, if the counts that we're interested in have some term that we really want to interpret our count relative to that, whether it's a unit time, person time at risk, number of total sample size, then what we want to do, and it's quite simple how to do this in R. The first thing we note is that we want to actually interpret not the expected value of the outcome, but the expected value of the outcome divided by the this relative term, whether it's monitoring time, person time at risk, or whatever. So in this case, Jeff was looking at the number of web hits originating from simply statistic relative to the total number of web hits. Okay, and he wants to model that as e to the beta naught plus beta 1 times the Julian gate. So he wants to model that proportion as being this log linear model. Well, if we take the log of both sides and we add, mess around a little bit, we see that we get the kind of a similar model to what we had before. We get the log of the outcome is the linear regression part, but that also it has this log offset with no coefficient. And that, it turns out, is all you have to do to add a term to add a rate or a proportion into a Poisson GLM. You just take whatever this relative denominator count or time or whatever it is that you want to consider and add it as a log offset in your linear model. Okay, so the easy way to add this offset into our linear model is just to use the term offset equals log visits plus 1. Remember, we have to add the plus 1 because we can't take the log of 0. remember we have to have family equals Poisson in the model statement here, and by default it assumes a log link, which is what we want. We haven't really covered any other kinds. So there's another way you can add the offset. I think you can add a plus O variable name in the actual model specification part on the right of the tilde, but this isn't just as easy to do it as an argument in the GLM function. Here Jeff gives the difference between the GLM1 fitted rates, which was, remember, to the outcome, to the number of web hits, where versus the GLM2 fitted rates, the assigned variable GLM2 fitted rates, which was the relative number of web hits originating from simply statistics. So these blue points are adjusted for the red points in a sense. And in this actually shows the fitted model relative to the data. There were a lot of zeros early on, and then it took off quite a bit. But this is the fitted model. The blue line is the fitted model, and the gray points are the actual data points. So you can get more information on log linear models and multi-way tables. And another very common problem that occurs in Poisson data is when the particular number 0 occurs way more often than it should. This is called zero inflation. Then the Poisson model would allow it to if it wants to fit the other counts. And so this is called zero inflation. And so there's a lot of different ways to handle zero inflation in Poisson data, but you need to think about that. In this case, we might be concerned with handling all of those zeros early on, though there's a temporal component to the zero inflation in this case, which makes it even a little bit more challenging to model it well. But the Jeff gives a package here that actually helps assist with modeling zero inflation. So I hope you enjoyed the lecture. That's the end of the lecture on Poisson data. To get you started, I'm hoping you can use a lot of your skills from binary logistic regression analysis and your skills from linear regression and multivariate regression, and just apply them directly in our Poisson examples here. Next lecture is the final lecture of the series. It's kind of a fun little lecture with just some kind of a bonus content of a smattering of things you can do with linear models that I think are kind of cool. So look forward to seeing you next time, and thanks for taking the class.